Hi, welcome back. So we previously talked about sequences, and now we're going to dive in a little deeper and talk about series. Well, a series is just the sum of the terms in a sequence. So a series is the sum of the terms in a sequence. So whereas with a sequence we had 1, 2, 3, 4, etc., etc. Now we would have 1 plus 2 plus 3 plus 4. And we have two different kinds of series. We have a finite series, which it's kind of exactly what it says. It's finite, it ends, and we would write that. You write your series as a summation with sigma, and you would go from n equals, let's say, 1 to 5 of, I don't know, whatever your series is, like a sub 1, right? Whatever that's defined as. Whereas an infinite series would just go on to infinity of a sub 1. And n can actually start anywhere. It doesn't really matter where it starts. It can start at 1, it can start at 5, it can start at 273. It doesn't really matter. But when we're calculating an infinite series, we can look at the sequence of partial sums to kind of see the pattern of what's happening with that series and determine whether or not that's going to converge or diverge. And we have a number of tests to do that. That's what this entire chapter is going to be about. Calculate or using tests to determine whether or not a series will converge or diverge. So these partial sums, which we denote as S of n, is just the sum of the first n terms, right? So it could be the first 5, the first 7, the first 862, whatever, and that's our partial sum. So let's actually work with these a little bit here. For both a sub n equals 1 over n and b sub n equals 1 over n squared, generate the sequence of partial sums s sub 1, s sub 2, s sub 3 to s sub n, then determine if the sequence converges or diverges. Okay, let's deal with our a sub n first. So that's going to be the sum from n equals 1 to infinity, and we're asked to start at 1 here, of 1 over n, right? Now I'm going to start writing that out a little bit and just see what that looks like. Well, that's going to be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus on and on and on to 1 over n, which would just go on forever, right? So we can also look and see what would our partial sum be. Well, our partial sum s sub 1, that would just be 1. Our partial sum s sub 2, that would be 3 halves if we add these up. Partial sum s sub 3, that would be 11 sixths. Our partial sum s sub 4, that would be 11 24ths. It looks like our partial sum s sub 5, that would be 137 over 60. And actually, sometimes it's easier to look at these as decimals. So I'm going to rewrite these as decimals. We have 1, 1.5, 1.833. I already did this on a calculator. 2.0833, 2.2833, 2.45, 2.592. So as this series is going on, you can kind of see, does it look like we're going to ever really converge to one number? You know, we're getting bigger and bigger and bigger and bigger and bigger and bigger. I don't think so. We're not. Actually, this series is going to diverge. And this is a special series that we're going to use. This is a special series. This series is going to diverge. This is a special series we're going to use. This is called the harmonic series. This is the harmonic series. So the harmonic series is written from n equals 1 to infinity of 1 over n. That goes to, it diverges, goes to infinity, all right? That equals infinity, right? And this is similar, you know, this is equivalent from 1 to infinity of 1 over x dx. If you found that integral, right, that would just keep going on forever and ever and ever as well, right? So this is the harmonic series, and you should be able to identify that, memorize that, and have that kind of in your mindset of calculus. I don't know how to word it, but I know what I mean, so hopefully you do as well. All right, let's do b sub n now. So we're given the sum from n equals 1 to infinity. I should say about the harmonic series, that can also start anywhere. The harmonic series is really defined by the 1 over n, not where n begins. Okay, back to our b sub n is 1, the sum of 1 to infinity of 1 over n squared. Well, let's write that out a little bit. So we've got 1 over 1 1 over 4, 1 over 9, 1 over 25. Okay, and if we add these up, and you don't have to write all of this, but I just find it helpful. And I'll just do decimals this time. So I'm going to have 1, S sub 2 would be 1.25, S sub 3 would be 1.4, oops, I skipped one, 1.3611, S sub 4 would be 1.423, and actually, I'm going to pull out my calculator here and show you something we can do. All right, so you can go here to alpha, window, and then the second button, or the, not second button, the second, so 2, and I'm going to type in, I'm using x's, but it doesn't matter what your variable, 1, 2. Now, if we were asked to find the partial sum of 6, we could, but we're going to infinity, so let's put a big number in there, like 200 of 1 over x squared. I've got too many parentheses, but, and let's see what this becomes. It's calculating, we get 1.6399, okay? So, like, I went out here, and I got 1.6399. Okay, well, what if I do the same thing, but instead of 200, I'm going to put 2,000, okay? Even closer to infinity, right? And this is going to calculate for a while, quite a while. I'll pause while it calculates. Okay, that did take a while. So 1 to 2,000 at 1.6444. Notice that I'm using a lot of decimal places here. I probably should be using even more, because as you can see, we're getting closer and closer and closer to 1.6444, something, you know, bigger and bigger and bigger. The more decimal places, the better. And also, how many do you have to have on the AP exam? You should know the answer to that question. So, do you think this is going to converge or diverge? Well, it looks to me, because here was at, you know, our 200, here was at 2,000, and we're not getting that much bigger. It looks like we're going to actually converge, and with this, we are going to converge. And so the series from n equals 1 to infinity of 1 over n squared converges, and it's approximately equal to 1.645. I don't want to say 1.644, because we know that it's actually bigger than that, right? But about 1.645 probably, something like that. And this is actually called, this is a type of series called a p-series, which I'll go over more as we go further into our lessons here. Okay, so let's talk about convergence and divergence. All right, so we're given the series n equals 1 to infinity of 3 over 2 to the n, and we want to determine if the series converges or diverges. Okay, so we're given 3 halves plus 3 fourths, 3 eighths, 3 sixteenths. You can see this going on here. All right, let's talk about this. It looks like we have like 1 and a half, right? Okay, so let me pause for a second here. Okay, so before we dive into this, let's imagine that we have 2 pennies, 1 cent, and another penny, 1 cent. And so I give you 1 penny, and actually we're going to start here. You can see, I'm going to erase this one, but we've got 1.5 pennies, right? And then we're going to add another quarter of a penny, then another quarter penny, and then another quarter penny, and then another quarter penny, And you can see that we're getting smaller and smaller and smaller and smaller and smaller amounts, like I can't even draw it anymore, so that you really aren't going to even ever fully have all that much penny, are you, right? So this is kind of how this type of a series works. This is a special series called a geometric series. So let's actually rewrite this. We've got the sum from n equals 1 to infinity of 3 over 2 to the n. We can rewrite that as 3 times the sum from n equals 1 to infinity of 1 over 2 to the n power, right? That makes sense, doesn't it? So if we have this, this is going to be exponential decay, right? It's getting smaller and smaller and smaller and smaller and smaller. So, 1 second. So if we're looking at this, this is actually, I'll write it over here, a series in the form n equals like 0 to infinity of a times r to the n. And this a is our constant, okay, so a is a constant, and r is a ratio, right? And that's what this 1/2 is here. And actually, or just so you, I mean, I have this written later, but you could also write it as n equals 1 to infinity of a times r to the n minus 1. Okay, doesn't really matter. But an a cannot equal 0. So this, if this r is less, or if the absolute value of r is greater than or equal to 1, we're going to diverge. But if the absolute value of r is less than 1, then we're going to converge. And actually, the cool thing about, these are called geometric series, the cool thing about geometric series is that we can actually find the sum. We can find the sum. S is going to be equal to a sub 1 over 1 minus r. So here, look again here. What's our ratio? Our ratio here is 1/2. R is equal to 1/2. The absolute value of 1/2 is equal to 1/2, which is less than 1. Therefore, this series converges. Right? But what does it converge to? Well, now we can find that. This series converges to a sub 1. Well, a sub 1 is going to be equal to 3 over 2 to the first power, which equals 3/2, over 1 minus r. So S is equal to 3/2 over 1 minus 1/2, which of course is 3/2 divided by 1/2, which is 3/2 times 2, which is equal to 3. So this series actually does converge, and it converges to 3. Okay, let's do another example. We're given this series. We want to determine if it converges or diverges. Okay, well, let's look at this one again. We have 3/2 to the n power. Well, you've got your sum here, n equals 1 to infinity, of 3/2 to the n power. It looks to me like this is yet again a geometric series. Well, what's our r? R is equal to 3/2. The absolute value of 3/2 is equal to 3/2. Is that greater than and equal to 1 or less than? Well, that's greater than or equal to 1. It's 1/2, so this diverges. So if it diverges, it diverges. I mean, and this really, you can see this is basically going to be exponential growth, right? So that makes sense. It would just keep growing forever. Whereas here, this would basically be exponential decay, and it would just keep decaying forever. So this leads us to, which I've kind of already talked about, this is the geometric series test. This is the first test that we're learning here. I think it's the first one. Maybe, yeah, it's our first one. Geometric series test that just outlines how we can calculate a geometric series. One of these, like a times r, what's down here, a times r to the n, or a times r to the n minus 1. So let's actually use the geometric series test to determine whether these following converge or diverge. So here we actually kind of already did this one. We can rewrite this as the sum of n equals 1 to infinity of 3 times 1 over 2 to the n, right? So r is going to be equal to 1/2, the absolute value of which is less than 1. So this converges by the geometric series test. And we can actually find, so our first term is going to be 3/2. We already did this, I think. 1 minus 1/2. Anyway, that's going to equal 3. All right, we've got this one here. And did I already do all these? Well, I think I did, but anyway. Our r here is 3/2, the absolute value which is greater than, oops, or equal to 1, doesn't matter. And so this diverges by the geometric series test. What about here? Here, our r is going to be equal to a negative 1/2. Well, the absolute value of that, this is equal to 1/2. The absolute value, so that's less than 1, so this converges, right, by the geometric series test. And we can actually find this too. So S is going to be equal to, looks like, well, here we actually start at 2. So we're going to be equal to 3/4 over 1 minus 1/2 is 3/2. That is ending up equal to 1/2. So this converges to 1/2. Okay? So we have another test for testing series, but this test only determines whether or not the series diverges. And this particular test is a good test to do first when you're looking at your series, because it's pretty simple. So if the limit as n approaches infinity of a sub n does not equal 0, then the series diverges. So we have to determine if they converge or diverge. If they converge, then we should find their sum. Well, we only can test with the nth term test if it diverges or not. So first we're going to calculate here our limit as n approaches infinity of 2n plus 3 over 3n minus 5. What would our limit there be? Well, it looks like our limit here would be 2/3. That does not equal 0, so this diverges. All right? Our limit here as n approaches infinity of n factorial over, sorry, this is a typo. This should be 2n factorial. 2n factorial plus 1. Well, these factorials are going to cancel out, so this is going to be equal to 1/2, which does not equal 0, so this diverges. Okay? Here, we have the sum. We're going to calculate our limit as n goes to infinity of 3 to the n minus 2 over 3 to the n. So basically, we have like 1's in front of here, right? So these are going to cancel out. So this is going to equal 1. This does not equal 0. So this diverges. All right? What about this? Well, our limit here, as n approaches infinity of 1 over 1.1 to the n, is going to become, well, that's actually going to be 0. Okay? So this does possibly converge, right? We don't know for sure that it converges, but we know, anyway, it doesn't necessarily diverge for sure. So we can actually calculate this. This is the same, this is a geometric series test, right? So R is equal to the absolute value, 1 over 1.1. That's, what? I have so many lines here. Absolute value of 1 over 1.1, which is equal to 1 divided by 1.1 equals 0.90909. Well, that's less than 1. So this converges according to the geometric series test. Converges by geometric series test. 2, S is equal to 0.90909 over 1 minus 1 over 1.1. And you can calculate that if you want, but I don't feel like it. So, all right. Okay, one more type of series I want to talk about is a telescoping, where did it go? Telescoping series. So a telescoping, I think it is. Telescoping? Anyway, telescoping series collapses to one term or just a few terms. So like here, we have 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4. You can see that these 1/2s would cancel out. These 1/3s would cancel out. And if this pattern continues, then they're going to collapse onto each other just like a telescope would, and you're going to be left with just a few terms, all right? So we can, if a series actually collapses to a finite sum, then it converges by that telescoping series test, all right? And the easiest way to do this is just to actually write them out. So here we have the sum of n equals 1 to infinity of 1 over 2n plus 1 minus 1 over 2n plus 3. So if we start writing this out, we're going to have 1/3 minus 1/5 plus 1/5, that's our first term, right? Plus 1/5 minus 1/7, that's our second term. I like to write a little note to myself there. Plus 1/7 minus 1/9, plus, it looks like this will go on and on. So these fifths are going to cancel out, these sevenths are going to cancel out. So all we're going to be left with, as we go on forever, is just 1/3. Okay, so this actually equals 1/3. All right, what about this one here? Well, if we write this out, we're going to end up having 1 minus 1/2, right? Because I could rewrite this, sorry, before I do that, as the sum from n equals 1 to infinity of, you would have to do your heavy side, that partial fractions, but I'm just going to do it for you. 1 over n plus negative 1 over n plus 1, right? And I found that using partial fractions, which we've done before. So this would become 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4 plus on and on and on. These are all going to cancel out. So we're just going to be left with 1. So that equals 1. Right? And we have another one here. I can rewrite this using partial fractions. And again, I'm just going to kind of do it. So this would be 1/2 over n plus 1 plus a negative 1/2 over n plus 3. So I can rewrite that again as 1/2 times the sum of n equals 1 to infinity of 1 over n plus 1 plus a negative 1 over n plus 3. Okay, so now I can start writing this out. I'm going to have 1/2 times, going to be a big bracket there. Looks like I'm going to have 1/2 minus 1/4 plus 1/3 minus 1/5. There's my first term, my second term, plus 1/4 minus 1/6 plus 1/5 minus 1/7, right? Plus, and I should add another one, 1/6 minus 1/8, right? On and on and on. So now I can kind of see these cancelings, 4s, 5s, 6s, so that I know my 7s and 8s will cancel because I've started to finally get some doubles here. So I really have this 1/3 and 1/2, okay? So now my sum, my telescoping series, is going to go to 1/2 times the quantity of 1/2 plus 1/3, which is just 1/2 times 5/6, which equals 5/12. So this series converges to 5/12. Okay, the last thing I want to talk about, and this is actually a problem on your homework, is how to do these, to find an a sub n given s sub n is equal to 7n over n plus 3. Okay, this is number 11 on your homework. Well, so a sub n is equal to s sub n minus s sub n minus 1, right? That makes sense. So we can actually calculate, we want to find a rule for a sub n given this. Well, let's do that. So a sub n is going to be equal to s sub n, which is 7n over n plus 3, minus s sub n plus minus 1, which is 7 times n minus 1 over n minus 1 plus 3. Okay, so let's expand on that a little bit. If I rewrite this, I'm going to have 7n over n plus 3 minus 7n minus 7 over n plus 2. Okay? So now I can kind of find a common denominator here. I'm going to have a 7n squared plus 14n minus 7n squared plus 14n minus 21, right, over n plus 3 times n plus 2. Well, these 7n's are going to cancel, n squareds, the 14's are going to cancel out. So I'm going to be left with a positive 21 over n plus 3 times n plus 2. And that is going to be equal to a sub n. All right? That's how we find that. All right. Any questions, leave them in the comments, and I look forward to seeing you in class. Bye.